In this video, we continue to make progress in our explanation of intermolecular interactions by talking about the dipole-dipole interaction. In prior videos, we have seen how the forces that cause the interaction between two ions can be captured by Coulomb's law, and then we'll move on to explain how the attraction of an ion with a dipole seems to have a modified version of Coulomb's law, in which here you have to introduce a dipole, and then you also have that the range of the interaction changes. Now the question then is, how would a dipole interaction with another dipole be represented using this type of expressions? Right, so let's think about two dipoles, and that would be HCl interacting with HCl. Okay, so again, notice that here you have two dipoles. Okay, those ones, negative and positive end, negative and positive end. So what you actually have is that the positive end of a molecule is well aligned with the negative end of the other molecule to be able to cause here stabilized interaction. Okay, so it turns out that the equation that tells you how these two dipoles interact when they are in this type of orientation is also very simple. It's just the product of the dipoles, okay, over 4 pi E naught and then R, but in this case you have a cubed right here. Okay, so similarities and differences with the ion-ion and ion-dipole equations. Again, notice that the numerator always contains the origin of the interaction. In this case, it's just the product of two dipoles. Okay, this is the dipole-dipole interaction. And the denominator contains a few constants and also the range of the interaction. Notice that as you go from ion-ion to the ion-dipole, the range goes from inverse r to inverse r squared, and here now we go to inverse r cubed. Okay, so what happens is that this dipole-dipole interaction is even shorter ranged than ion-ion and ion-dipole. Okay, so these tend to die off fairly soon. As soon as you separate these two dipoles a little bit in space, then the attraction between them will actually disappear quite quickly. Right now, something to notice here is that this expression only works if the orientation of the dipole moments is as we have written it. Okay, if you actually had a different type of orientation, then the equation changes. Okay, but we're not going to see how. Okay, so for example, if you have here now that the alignment of the two dipole moments is something like this, clearly this wouldn't be an attractive interaction, it would be a repulsive interaction, right? So you wouldn't have a negative sign in the energy, it should be a positive sign. Okay, so again, this equation would need to be modified, but we're not going to see how that works. Okay, or there can be any other type of interactions, right? You could actually have that maybe the two molecules are aligned like this. Okay, HCl, where here you have a positive with a negative, and then you see that, well, these could attract each other, that could attract each other, but that would repel each other, that would repel each other. And again, what this tells you is that essentially this equation depends on the angle between the two dipole moments, right? The way that we've written it simply indicates that the dipoles are oriented in the most favorable orientation. Okay, and again, if you have other type of orientations, okay, then you will have to modify this equation slightly. But again, we're not interested in that. We're simply interested in what causes the interaction and the range of the interaction. All right, so this equation also only applies to the gas phase. Okay, so it turns out that when you're in a solution, things become a little different. Okay, so what will happen in solution is that, well, if you have this HCl oriented this way, with this dipole moment like that, okay, there might be instantaneously another HCl molecule oriented in the correct orientation. Again, this is quite stabilizing. But of course, if you're in solution, what happens is that there's thermal motion, and then there's going to be collisions with neighboring molecules, perhaps solvent, okay, that are going to knock these two molecules out of orientation. Okay, so sometimes you will be in this orientation, but if you examine this a little bit later, then maybe the orientation is something like this. Okay, the other way around. Okay, CLH. Okay, and anything can happen in between. Okay, so there's going to be some sort of averaging of all of the orientations that you can have. Again, because thermal motion tends to randomize the interactions. This will feature quite prominently. That's the most attractive. So this will actually be seen quite frequently this might be more rare, okay, but it will also take place. Well, it turns out that there's actually a way to obtain an average, okay, of the interaction, all positive and the ones that are attractive, the ones that are repulsive, an average of all those in solution, okay, which is a modification of that expression as well. And that expression is interesting for the following reason. Okay, for one, there's a proportionality constant that we're not going to see. We're going to call this A. Okay, and then you have that. Now you will have the two dipole moments. Okay, but they were going to be squared. Okay, and in the denominator, you're going to have that the range now goes all the way to the sixth. Okay, and also this force or this attraction depends on the temperature. All right. Let's actually examine then the temperature dependence. Notice that if the temperature goes up, okay, the attraction between the two molecules goes down. Okay, and that is because when you elevate the temperature, okay, you have more thermal motion, and that thermal motion is going to be able to knock out these attractive interactions very well. Okay, so you're going to experience an average smaller attraction, and if again you're randomizing those positive orientations, those favorable orientations, quite vigorously. Okay, now what about the rest? Well, the rest, what happens if the dipoles go squared, but this is actually very important. You have here an R inverse R to the sixth dependence, and this is something key, because what we know as van der Waals interactions, okay, are attractive forces that depend on the inverse to the sixth dependence of the distance. Okay, so again, this is the first time that we actually have seen something that is called a van der Waals interaction, and we will see how, as we go through the list of types of interactions that we have to explore here, there will be other interactions that also have an inverse R to the sixth dependence. Again, all of those are called van der Waals interactions. Okay, so to summarize this video, we actually are studying here dipole-dipole interactions. We have seen what the attraction is when those dipoles are oriented in the right way and in the gas phase. And we have seen that how in solution things can get a little more complicated, okay, because there's thermal motion that tends to randomize the orientations. And even then, we can actually come up with an average way to calculate the attraction energy, which is very interesting because it depends on temperature, okay, and it also depends on the inverse R6 dependence, which is the first time that we have seen a van der Waals interaction.